Having a recording going on. All right, so good afternoon to those who just came in. So the last day, we looked at what we call the little t formula, the little t identities connecting sine, cosine, and tangent, right? And uh, pen, pen, okay, that's my pen working there. Okay, so as I was saying, last time we got the little t formula that would solve, let's say you have this equal to some number, 5 or something like that. Yeah. If you have an equation of this sort, the little t formula that we had, we could just take the cos theta, replace it with a set of uh, things with t inside, the sine theta, same thing, set of t's, and then we have everything in terms of t, and then you do some solid algebra, and then you can be able to solve such an equation, right? Um, if you took the time during the week or the weekend and tried any of them, you'll see the algebra is rather tough. It takes some doing, and there's always that need to find different ways of solving different types of problems. And there's where we got to take a lesson. That's how new mathematics is created all the time, right? There's there's some way of doing something, and somebody just has to say, look, could we do this another way, right? And find another way to do it, right? I mean, we can actually build on mathematics that is lying around, or we can create whole new mathematics, right? Um, it's interesting. I don't know if you all are movie lovers, and so anybody anybody saw the movie Hidden Figures? Anybody saw that movie?
Yes, sir.
Oh, you saw that? Okay. Anybody else
Yes,
saw it? Hidden Figures?
enjoyed it.
I didn't hear that response.
I was saying that I actually enjoyed the movie.
Oh, okay, yes. And it's interesting in that movie, very inspirational, huh? Um, when you think of people, flying into space and all of that, what comes to mind? When you think of who sends all the rockets and so to space and do all the work, the engineering and so, what color people you think comes to mind right away? What color comes to mind? You're afraid? You all heard me? You all heard the question?
No, sir, please repeat.
I
I
was
was
saying that when
switching
you think
devices.
of people who, just like how when you think of mathematicians and so, when you think of those who, work at NASA and sends rockets to space and so, sometimes you don't think of, you always in your mind think, well, these got to be white guys. But that movie brings out, oh, by the way, that's a true story, right? That a lot of black women were involved. And notice, even the department where they were doing the mathematics, because taking something into space, building a vehicle and working out the trajectory, the exit and the entrance trajectory, and so for the rocket is a lot of mathematics, right? And usually you don't think that well, black women were involved with that, but that movie brought out the truth, right? That it was a set of black women, lots of them too, were involved in a whole the story centered on about 4 of them. But you see how many were there, right? and they were involved in I remember, and while I'm talking about new mathematics, um, I'm re, I'm remembering the scene when they thought they didn't have any kind of mathematics that would help them to work out the trajectory of the flight, that this thing would go into orbit. And one of the girls actually told the head of the whole department that, you know what, there is some old mathematics lying around that can help us. And they were like, what? And they gave her the chalk and said, go up. And she climbed up the ladder and she started to explain that there was some old mathematics lying around that would make it possible. And they were all amazed. There's this guy from the Big Bang Theory. He's more of the villain, like, or the antagonist in the movie. He was not pleased that he didn't come up with it. Sometimes the brightest guy in the room thinks if he don't come up with it, but he's not going to support it, he's going to undermine the others and so on. But yet he had to swallow his pride and realize that these girls were very brilliant, you know. And they did come up, they showed them the mathematics that it will work, and that's what they used, right? Yeah.
In addition to that,
Uh-huh.
even the guy that was going to be flying the rocket, he trusted her math against anybody else's. So he
Yes,
wanted her to double check everything before he actually launched.
yes, very good. And that's to show basically, in other words, you're saying that I'm willing to risk my life on your mathematics.
Basically, sir,
I,
indeed.
I I watch those movies for sheer inspiration. I really enjoy them. I actually have it up. I have a movie site, my own, where I censor movies and put them up. So I have that one there. So sometimes I share it with students so that they can enjoy. Yeah, okay, back to this. So as we said, there was an approach, right, where you could have converted. Let's say you have this expression equal to something, right? You could have used the little t formula um, to solve such a problem. However, there is another approach, right? And what this approach involves is first taking an expression of this sort and writing it as r cos of theta minus alpha. It doesn't have to be cos, it can be sine, right? It can also be sine, right? You can have r sine theta minus alpha. You can also have theta plus alpha in here. It doesn't have to always be minus alpha, right? So keep those things in mind. You can have sine here. You can also have a minus sign over here, right? Good. So how do we do that? At least let's use the one with the cos, right? So what we're going to do, we're going to take r cos theta minus alpha and expand it. And this is what you'll get, right? So you expand this using what you call the compound identity, right? So when you expand it, you get that, right? And if you were to take r and multiply it in here, you'll have what? You'll have r cos theta cos alpha plus r sine theta sine alpha. And if you were to do something called comparing coefficients, right? So watch here. This cos theta matches with this cos theta. It therefore means that A is equals to R cos alpha. That's what they have here. Similarly, okay, if this sine theta matches with this sine theta, then B matches up with R sine alpha. And that's what you see here, right? You do a little division, you divide this one by this one, and you get tan alpha equal B over A. On B over A, B and A are going to be numbers, right? 1 to 5 minus 1, all kinds of things, right? It's going to be numbers. So tan alpha is going to be B over A. From that, you can actually get alpha. You have to only just and inverse the whole thing, right? Good. And of course, if you want to find the value of R, well, you can use this formula, right? R equal um, square root of a squared plus b squared, right? So you can actually get that. Well, this is by the way, too, you can get cos alpha from it. You can get anything, your sine alpha, all kinds of things, right? Good. So R is going to be given by this value here. Right? And again, I told you A and B are going to be some numbers, 1 and 2 and -1 and -5 and all kinds of things, right? So now that you have alpha and R, we can now write um, A cos theta plus B sin theta in the form. Remember, we got R and we got alpha, right? From this process I just described here. And well, what can you do with it? You can do a number of things. You can sketch graphs, you can solve equations and all of that, right? You'll see it in just a moment. Tell me if you're not following it. Anything you want me to clarify and so. Okay, good. So, as I said, we can now write an expression of this sort in this form, where R is given by this formula, and alpha, which is an angle, is given by arctan of B over E. Right? What we're going to do, we're going to do an example to illustrate how we can do this, and then you'll see the possibilities that will open up because of being able to write A cos theta plus B sin theta in that form, right? R cos, it could be sine, as I said, bracket theta minus alpha or plus alpha, right? You'll see the possibility. So let's take an example. So they start by asking you to express 3 cos theta plus 4 sin theta in this form. They're exact. They didn't change anything. They didn't change the cos, the sign, or the minus sign into plus or anything. And you will ask, well, why? Why? Well, textbook writing again, right? The people know that when you remove or when you expand this bracket here, cos of theta minus alpha, there's going to be a plus sign in the middle here because of the nature of the identity. And that matches the plus sign here, See, if you don't put a plus and you put a plus sign in there, you're going to get a minus there. See? So keep those things in mind. You figure those out from experience, right? If you were to try a lot of these and you try some out, why I got to write R cos and theta minus alpha? Why don't I put a plus sign here? Right? And you will soon figure out too that if you were to change this to sign, you will have to change that to a plus, right? You will figure that out over time, doing this over and over. As I said, I've been doing this thing from so long. I was telling a couple of colleagues, and I actually did it. If you were to count how many times we write out the solution to the problems teaching all these courses over the years, and you yourself, you know, at school, you write out the solution of problems. Let's say you're teaching fifth form, you've been doing it for 10 years, you know? Every time you write a problem, you erase the thing. You know how much problems, how many times you solve that one problem. You would believe me, I've been doing this thing since 19, but it's really 88. I wrote exam in 89. I've been doing this thing since then. And I've been solving this problem almost every year, you know? And therefore, why not? I was telling a colleague of mine, why we don't document these solutions? Document them and you know, maybe create a solution manual or something. That's every year we just solve the problem and erase the whole thing. Think of yourself in school. Every time you solve a problem, you erase the thing, right? Yeah. There's AI now that can, but you still have to check the solution of the AI, right? Because lots of times they're wrong. So keep that in mind. Depends on how well trained the AI is for mathematics and particular areas in mathematics and so on. Right? But yeah, you do these problems over and over, you get it done. So I actually took the calculus course I'm teaching and I made it into a video course. So this year, the teachers who did the course with me, I didn't have, well, they were invited to come to a lecture I have in the afternoon. They never came. So they learned the course without ever coming to a class. I just give them the playlist in order, I give them the notes. All they do is come and write the test. Yeah. Um, Automation of education is happening all over now, right? I'm doing a PhD at, that PhD is fully automated. I've never seen nobody ever tell me anything, ask me anything. You just read the thing and submit the work. Coursera, if you all ever did any course on Coursera, it's totally automated. Totally automated. All right, yeah, let me go back to this. So we're gonna take this and we're gonna write it in that form, right? So again, you take this here, you take this and you expand it and you equate it to that, right? That's what we do here. And then we compare coefficients. So R cos alpha is 3. Um, R sine alpha is going to be equal to 4, right? By equating coefficients. You do the division and you'll see that tan alpha is 4 over 3. And R, we said, is the square root of 3 squared plus 4 squared, which is 5, right? Of course, the author used some nice numbers to get nice answers, right? You can actually find this value, right? You can find this value. It's always an ugly decimal. So that is why very often you see that they'll write it in this form. That this here is equal to 5 cos theta minus alpha. And they'll tell you that alpha is arctan of 4 over 3. You don't have to do this. You can write in the number there, right? But very often in the textbook, to make things look nice, to spoil the beautiful, looks of this. Instead of writing minus, God knows what this is, arctan of 4 over 3. It will look like a horrible decimal here. So you say that it's equal to this, where alpha is equal to arctan of 4 over 3. So we already write it here, right? We already have this in this form. That's that. We can do so much more with this, right? As I said, you'll see how we use it to solve equations, draw graphs, and so on, just a moment. And here they're telling you that, yeah, you don't have to use cos in order to say you can use r sine theta plus alpha. I just said that, right? So again, you expand r sine theta plus alpha, you get this equal to that, and you equate the coefficients, right? So again, you will have, in this case, r sine alpha equal A, and r cos alpha equal B. So notice you're dividing r sine alpha by r cos alpha. You get tan alpha equal A over B. So you have to be careful of that little switch around, right? When you were dealing with the cos was, you have to divide was B over, what was it? B over A, right? Was it? Yeah, B over A. You see here, B over A. In this case, it's A over B, right? So you got to be conscious of when you create the tan alpha, where A and B is, right? So just be careful with that. But you can't go wrong with the value of R. R is always the square root of A squared plus B squared. So if you were to do that with the same problem, notice they'll tell you that the value of alpha is not going to be the same, depending on whether you use cos or sine, right? Yeah. And they're telling you all the variations that you can try, right? You can, in your own free time, try these variations. Try these variations. Right? Don't play lazy, just spend some time And, see how you can write this in this form using this um, compound angle form here. Sine, notice they have sine with a minus there, right? So use cos, then use sine, use cos, then sine, sine, then cos, and see what happens, right? A lot will come out, right? If I were to just tell you stuff and work example, nothing helps you more than when you try the thing, even go wrong and struggle to arrive at the answer, right? When you struggle to achieve something, you value it more, it remains with you more, right? You can tell stories of what you did to get this thing. Right? When you just give me the teacher, just tell you the answer, tell you the answer, tell you the answer. No brain development takes place, right? You don't grow cognitively, and all you're doing is you're being spoon fed like a baby, right? And babies don't really develop if they don't start eating solid food, right? Yeah. Good. So we are saying now we can take this thing, this A cos theta plus B sine theta, and we can actually get the graph knowing what we know now, right? Good. So let's see, right? So all of this is just some basic information about the cos curve and the sine curve and the good. Let's take one. So I think let me go to actually. All right, look at this one. So they wanted to sketch the graph of the function 3 cos theta plus 4 sine theta. I wish it had a whole minus 360 to 360. So, all right, go with what you have. So you take this 3 cos theta plus 4 sine theta, and you write it in the form r cos of theta minus alpha, right? So that's what we're going to do. We're going to write this in this form. So you get r is 5. I think we did it before, right? Tan alpha is 4/3, therefore alpha is 53.13. So basically, this thing is equal to 5 cos of theta minus 53.13, right? And what they're telling you here is that the graph is going to be the cos curve that you would increase the amplitude or multiply the amplitude by 5. You know the cos curve is from -1 to 1, right? Positive 1. That's the amplitude, right? The amplitude is 1. But because there's a 5 in front now, your graph is going to actually come up to the point of +5, right? And well, it's supposed to go down back to -5 here. Good. The next thing that will happen is that the cos curve, because there's a minus 53.13, what will happen is the cos curve is actually going to be shifted 53.13 degrees in the positive direction, right? So when there is a plus 53.13, you would have moved the curve to the negative side. But when there's a negative 53.13, you actually have to move the curve, the cos curve, 53 degrees to the positive direction. And this is the graph here. So knowing this here, knowing how to convert an expression like this into this can help you to pick out the graph, right? Or sketch the graphs out, right? You will know the new amplitude. You will know the phase shift from whatever is here, right? And you can now draw your graph. I guess you all did all of this stuff in the previous course and so on, right? Where you did phase shift. You were supposed to do, all right, like if I give you a curve of this form, 1 second, let me go through this. Let's say you have a curve of this form. Fx equal to, let's say, 2 sine, let's go with 2 theta, maybe, should go with, let's go with 3 here, and 2 minus, let's say, 30 degrees. Even maybe I could add on something plus 4. So I guess you remember, you have to take, first of all, sine 2 theta, whatever it is, right? And then you will actually have to do a phase shift of 30 degrees. But I think the phase shift will be minus 30, which is 30 over 2. It will be a 15-degree phase shift, right? Minus b over a. That's this number over that, right? Yeah. So you have a phase shift of 15 degrees. The amplitude would actually be multiplied by 3. And the whole graph will have to be lifted up vertically upwards. Just move the whole graph 4 units up, right? So I'll remember that sort of thing from the previous course. Some revision of that. You have to know it for this course, but you know that little bit about phase shift, you know, notice here, it was a phase shift of 53 degrees. You have to know that when you sketch your normal cost curve, how you will shift the graph. Right, that's important. Good. Now let's use it now to solve maybe an equation, right? Let's go to the equation now. So look here, you have an equation. Sine theta plus 2 cos theta equal 1. Now, as I said, you could use your little t formula, right? And solve this. Not algebra yet, right? But this is just an alternative approach now, where you can use your knowledge of this transformation that we just talked about, right? To be able to solve the equation. So we're taking this and we're equating it to this here, which when expanded gives you this, right? We equating the two. And you, of course, comparing coefficients. So 2, r cos theta, r cos alpha is going to be equivalent to 2, right? Because cos theta and cos theta matches, right? And r cos alpha matches to 2, that one. And then this sine theta matches with that. So r sine alpha will match this 1 in front here. That's why you have that. Then you divide this by that. So you get tan alpha equal 1 over 2. And you can actually get the angle, right? You can actually get the angle of alpha. You just find tan inverse of a half. You get some angle, right? And you can get the value of r. R is simply going to be the square root of 2 square plus 1 square, which is root 5. Now you can write this here. So notice they're not putting in the value of alpha. You can do that. That's not a problem, right? So you put it there now. So we got r. We got alpha. We're not putting in the value. At least this right that doesn't, right? And you start your solution now. You take this over, you divide, get this. What do we do next? Right? So you cos inverse both sides. So you end up with theta minus alpha equal 360n plus or minus 63.43. This is the general solution for cosine, right? I guess you recognize that. And remember, you know alpha because you will find tan inverse of a half. So you will do that. And well, that's what you're doing, right? Put in the alpha value here, right? Look, it's 26.57. And then you add it to positive 63.49. You get this. And then you subtract it from 63.49 and you get that. So these are your general solution, right? But I think they don't want a general solution. They want the values between 0 and 360, right? So to do that now, you will put in some values for n. You try some values for n. Like you can start from -1 or -2 if you want. Well, the author is saying n equals 0 and 1 will give you all your answers, right? But remember, you don't know that. If you're working a problem like this from scratch, you might have to try n equal -1, then 0, then 1. But you have to try -2 and 2. But with experience, you will know that, oh, I don't have to go so far as -2 and 2. You know, maybe -1, 0, and 1 will work. And when you try those values to n, you will find that, well, oh, these are the only solutions. So here it is, an alternative approach to solving equations of the sort a sine theta plus b cos theta equal to some value, right? So where are we now? Good. So here it is. We're using the little t formula to solve, well, to actually write everything, what is it, express this in terms of tan theta. Right? So this is going backward. I think we did the little t formula already. Where are we here? Let me just go through an example more or two, right? Good. So, all right. First, you're taking this is a lot of algebra. Take this and this, right? And you want to write that in terms of t, right? So I think we got a formula like that already, right? Where t is tan theta, right? So 1 minus sine 2 theta will be this. So you do some algebra and you get this, right? You know you do that, right? So write this one as 1 plus t squared over 1 plus t squared. You know, that sort of thing. You get that. And it simplifies to that when you finish. Similarly, you do this, that's for the denominator. You end up with that. Then you do the division, and you will end up with this. And then you square root it, and you will get, well, when you square root it, this square sign is going to go, and you're left with that. But remember, t is tan theta. That's what you can see, right? Follow that? I know, okay. You remember there was a thing like this, okay, where sine theta, this might confuse you, is equals to this. But in that case, tan t was tan theta upon 2. So notice now we're having 2 theta there. So tan t is not going to be theta upon 2, but tan theta, right? I don't know if that puzzled anyone. Uh, for anybody who that puzzled, uh, that's the explanation here. All kinds of problems they can come up with, right? Here it is, they're comparing the two methods now. Solve this equation using the half angle formula. That's the little t formula, right? We're talking about. And then use the compound angle transformation. That's the thing where you have like r cos of theta minus alpha. So yeah. So let's try to solve it both ways. You take this, right? And you write it in terms of the t. Right? So you can jump in the step now, right? Like down here, you're not gonna write root 3 times t over 1 plus t squared. You just put in the root 3 right away, right? You just throw it in. And then the denominators are the same, so you just Um, subtract that numerator there, you get this. Take over this and multiply the 1, you get that. So do your little, your manipulation and you get this, right? In this case, you put, okay, 2t equals 0, which implies that t equals 0, that's one solution. Or t plus root 3 is equal to 0. From that, you get another solution, right? So from that, you get two solutions. You get, from this, you get this one. And from this, you get that one. So tan theta over 2 is either 0 or minus root 3. So we're not done yet. You got to solve for theta, right? That's what you asked for. And you want a general solution. So, okay, good. From that, theta over 2. Remember, you're doing with what? Tan theta over 2 equals 0, right? Well, 0 will be the solution. And theta over 2 equals minus root 3. The principal value is going to be minus pi over 3. Calculator will give you that, right? So these are the general solutions, right? These are the two general solutions. Probably remember the general solution for tan, right? And you just multiply everything by 2 now, because you have to multiply this by 2 and that by 2. You will get these answers. You'll get these answers. Good. So here you have the two general solutions using the little t method. Now let's use the transformation now. Compound angle transformation we're talking about. So you want to transform this into something looking like that, right? Good. So notice when there's a minus there, you use a plus in here, right? Because of the peculiarity of the compound angle, right? You expand it, you end up with a minus here, right? You expand it. So you compare the coefficients again, right? And you get r cos alpha will be this one in front here. And r sin theta is going to be r sin alpha is going to be this root 3 down here, right? So you divide this by that, you get tan alpha equal root 3. I guess you can get alpha from that, right? Just find tan inverse of alpha upon 3 and the calculator will give you the answer. And r will be equal to, well, what? Root 3 squared plus 1 squared, which will give you root 4, which is 2, right? Yeah. So we know r. So we can now write back this equation here. Cos theta minus root 3 sin theta as 2 cos theta plus pi over 3, right? Because you find tan inverse from this. You get a nice number. Notice they put it in now because alpha happens to be a nice number, right? So with this now you can solve, right? We were successful in writing this as this. And from here we can solve, take over the 2, you get that. Cos inverse both sides, right? So you get theta plus pi over 3. Cos inverse of a half is also pi over 3. Right? So they say the principal value is this. And you know the general solution for cos, right? The general solution for cos is 2n pi plus or minus pi over 3, right? Plus or minus the PV, right? PV. So all you got to do now, you got to make theta the subject by taking this over and subtracting. And that's what they did here. You subtract this from positive pi over 3, that will leave you with that. Minus pi over 3 minus pi over 3 will give you minus 2 pi over 3. So you have the two general solutions. So regardless of which method you use, you get the same solution. You can recall. This is the same solution we got when we use the little t. Like I'm just erasing all this stuff, And I think I'll make all of these things into some videos that, well, all of this is going to, you can try all of these, right? In your own sweet time. Oh, this is an example. Sorry, let me go through this example. All right. So they want you to express this here in this form and give the values of R and alpha. And then show that this expression here is either less than or equal to 20, right? And then they tell you to find the minimum value. And okay, they even want you to sketch this graph here, right? Quite a bit of stuff there. Let's go through this one by one. Take it one by one. Good. So let's start by, we got to write this thing in the form r sine theta plus alpha. Right? So you equate coefficients, you get your r and your alpha. It's actually an angle, an horrible looking angle, right? So we can now write 5 sine theta plus 12 cos theta is identical to 13 sine theta plus, and alpha is really 67.38, right? Good. So we know that anything with sine, right? The sine function, regardless of where the angle is, it's between -1 and 1. We all know that, right? All of us know the sine curve kind of oscillates between -1 and 1. Good. So if this expression is equal to 13 times sine of something, well then this here, if you multiply by 13, then the expression 13 sine theta plus alpha now oscillates between -13 and positive 13, right? And remember, this is identical to this here. So we can rightly say that 5 sine theta plus 12 cos theta oscillates between -13 and 13. Now they ask you to say, well, okay, show that this here plus 7 has a, what is it, a maximum value of 20 or something like that? Yeah, look at it here. So you add 7 throughout. So you add 7 here. And what happens? This becomes that, and that becomes that. So they're telling you then that this is what we have to prove. That 5 sine theta plus 12 cos theta plus 7 is either 20 or less, right? Less than or equal to 20, right? And the minimum value, notice the minimum value is -6, so we take that out. So they now want you to graph, they want you to graph 1 over that thing, not 13 sine theta plus alpha. They want you to graph 1 over that. However, before you can graph this, what you call reciprocal graph, you must be able to graph this one first. You have to graph this 13 sine theta plus alpha first, right? And that's what they're doing here. So first, oh, they didn't. Oh, let me obstruct myself, and I have to let me go. I want to use Desmos to show you how they actually graph. What is it? 1 over 5 sine theta plus 12 cos theta, right? Which is identical to 13 sine of theta plus alpha. I want to stop sharing just to go to a graphing software to show you. They kind of jump straight to the graph here. I want to show you how they arrive here, right? I want to show you how they arrive here. So bear with me. I'm going to stop sharing for a moment, right? I'll stop sharing. And I'm going to go to a graphing software to show you something. Desmos, you all probably heard of Desmos graphing calculator. Do you use it? You always use this graphing calculator. Desmond, hmm? Y equals 13 times. I hear no response is so, is what was it? What was the angle? Anybody can remember? Stop shooting for a moment. Let me see. What was the angle? 67.3 degrees out. So the theta minus 67.38. Why don't I just use 67? I just want to illustrate. So this is the original curve. Change the but so I want to come now and just show you what the other one will look like. Y equals 1 over right? It's the same.
So there is two equal signs, right?
Oh, I have to equal sign. Thank you. Somebody pay attention. Oh my side. Oh, what was that? Theta, theta minus, what is it, 67? I use 67. I wouldn't use the decimal. Because I just want to illustrate what you really do when you when you one more. I just want to see what it is you want to do. Yeah, all right, well, yeah. That's right. Cool. So I want you to look here. The graph of 13 sine theta minus, I didn't use the decimal, right? Minus 67 degrees is this graph here, right? The red. You're seeing the red, right? Good. So the other one now, the reciprocal of that, how do you draw that, right? And there's a shortcut to drawing it, right? What you do, where this graph has a maximum here, let me see, but I think I can annotate that graph. Give me a second. So this is how you actually, so where this graph has a maximum, the reciprocal graph will have a minimum, right? Now this graph, because of scale, I can, down here is 1 over 13, right? 1 over 13. I'm talking with the y value. Because the graph is so, the scale, let's see if I can, I have to stop. Because down here is actually, let me stop. Down here is 30, right? 30. So the minimum here on the reciprocal graph will be 1 over 30, right? Now where the graph is, notice, heading towards 0, where the graph is heading towards 0, the reciprocal graph will actually be heading towards infinity, right? So where you see minus, I wonder what that is, minus 300. Yeah. Where it's heading to minus 300 is actually heading to infinity, right? And down here, where the minus 100 is, the graph was actually approaching 0 here, right? Instead of the reciprocal graph, it's going to head towards infinity. Down here, where there is a minimum, the graph here would have a maximum. Because this graph, the scale is so tiny, that down here, this is supposed to be negative 1 over 13, right? Yes, right? So look here, where the graph is heading towards 0 there, this graph is going to actually head towards infinity. Where this graph is heading towards 0 here, this graph is going to head towards infinity. Where there is a maximum here, there's going to be a minimum here, right? So there's that rule when you want to sketch reciprocal graphs, right? How you do it. There's some rules like, okay, when the original graph is heading to a maximum, the reciprocal graph is going to head to a minimum, right? When the original graph is a minimum, the reciprocal graph will have a maximum. Where the graph is heading to 0, right? The reciprocal graph is going to head to infinity, right? And depends on which direction it's coming from. Like here, it's heading to 0 from the positive side. This one will head to 0 to infinity on the positive side. So here the graph is heading to 0 from the negative side. Well, the graph is going to go towards infinity to the negative side. That sort of thing, right? So that's why I want to show you in this mode the original graph and the reciprocal, right? You can always YouTube a little explanation and some examples, and you will see some more being done of reciprocal graphs, how you draw it, right? General rule to how you go about doing it. Well, you don't have to erase all it. I want to go back to the note, right? A second. That's what they did. So with them, they actually use a scale that is appropriate here. On Desmos, I use a scale that the 113 and the minus 113 wasn't shown. It was as though the graph actually kissed the x-axis. But no, it didn't, right? It was the scale I used that didn't show it. Yeah. I mean, this one was a very involved one, right? Yeah, I expect I'll ask you something like this in a test, right? This is the kind of thing you do for, as I said, an assignment, or you take a long time, probably for your own brain development, you try a problem like this. Good. So I encourage you to try some of these for your own, if you can spend some time and try some of these, right? This exercise here, the answers are with you, right? Good. So could we take a break there? Could we take a break? And then we'll
Yes,
come
sir.
to the factor formulae.
Sounds good.
Take a break. We come back at 5:10. Resume the record. Okay, good. So this is our last piece for this the factor formula. So what's this all about? Right? The factor formula basically is you're trying to write a sum of trigonometric function as a product and vice versa. Just like how you all know algebra, right? You write, let's say you got x squared plus x. You can write that as x bracket x plus 1 or something like that, right? Yeah. You can take the sum or difference, right, and write it as a product. And you can take the product and write it back as a sum or a difference. Same thing here. Same thing here, right? We have a very nice exercise here. If you can take some time on your own and go through this whole process of how they came up with the factor formula, right? This is not a factor formula. This is the process to go through and get it, right? So this is the factor formula here. But it's not one um, what am I saying? It's not one identity, the whole series of them, right? So if you here, you have a sum, and then it's now written as a product. You see that? You have a difference, it's written as a product. You have a sum, it's written as a product. You have a difference, you write it as a product, right? So that's it. Basically, that's the factor formula, right? And you don't have to worry about memorizing all of this, right? Because you will have a open book test, right? So what is this P and the Q and all of that? Well, notice what the P and Q's are, right? Yeah. So P is equal to A plus B, Q is equal to A minus B. That's from the original compound angle formula, right? Take some time, you go back to this here and walk it through how they got it, right? So you notice you have sine A plus B is this, sine A minus B is that, right? So what you do? You add the two, you will get this here equal that, right? Subtracting, you will get that. You do the same thing for costs and costs, right? Adding, subtracting, and so on. And when you finish doing all of that, you take, instead of writing A plus B, you put P, A minus B, you put Q, right? So up here where you see the A plus B, this is P, the A minus B is Q, right? You do that exercise. And when you transform everything, you see that A is half P plus Q, B is half P minus Q. So as you notice up here, you have, while over here, you might have A plus B and A minus B. Over here, you just have A and you have B. You have A, you have B, right? So where A plus B is P, A minus B is Q. A, notice it says, is half P plus Q, right? You put half P plus Q over 2, and B is P minus Q over half, P minus Q over 2. And that's where you got all of these. That's where you got all of these. Right? No need to memorize them. As I said, you will have an open book test, or you will have a formula sheet that you will compile and get. So you don't have to worry about memorizing that. What you need to know is being able to use them to maybe prove an identity or solve some equation or something of the sort, right? Yes, they're going to be back order. Let's use it. Let's use it. Very simple example, right? So you want to here express this is a difference as a product. Well, right? This is like your P and that's like your Q, the thing. So what you do? Add the 2, you divide by 2, down here subtract the 2 and divide by 2. Right? This is factor formula. They refer to equation 6 or the identity 6, and you get this, right? And when you simplify that, you will get 5 theta. And you simplify that, you will get theta. Right? The other way around, you have a product here, and you want to write it as a sum. Right? So this is what. Think of this as seven theta and 2 theta. This is going to be P plus Q upon 2 down, you got P minus 2 upon Q, right? So if you want to, all right, if you can't remember, I'll go back here and look here, right? Look at what A and B is, right? If you can't remember that, it'll refer you back to this one. It'll refer you back to this one, right? So you take this, plus that, that's what's going here. And down here, that this minus that, right? Once you get the identity, you just go back to it, see which one will work, and you apply it. There are some ways here. You will read this as to how you can remember the identities. I mean, as I said, you might not want to strain your brain to remember anything. You might simply go back to your formula sheet, right? But as I said, if you work a couple well of these, you will know the techniques that will suit the different types of problems, right? Because some of these can be very, very difficult, right? Like, let's start with this one. These are not very easy to do, right? Now look at this one. They ask you to prove that sine A plus sine B over cos A plus cos B is identical to tan of A plus B over 2. Right? And the problem isn't finished here. They said that if A, B, and C are the angles of a triangle, deduce that sine A plus sine B, that's the same thing here, cos A plus cos B is equals to cot of C over 2, right? We got to prove something, then we got to do some, play around with a triangle to make a certain deduction from it, right? So let's see. Let's start with the proof maybe. All right. So you take the left-hand side. This is a sum in the numerator, and there's a sum in the denominator. You use the factor formula, right? And what do you end up with? I guess you can see, well, this cancels with that. And sine over cos, well, the 2 and the 2 will cancel. It's the same as tan. So tan or A plus B over 2. So simple, name. All right. Yeah, simple. I promise you it will be hard, but this one is too simple. Not all of them will be this simple. It just so happens that and that's the thing with textbook writing, I like do the easy one. Yeah. All right, let's go to the other part where if A, B, and C are the angles of a triangle, deduce that sine A plus sine B over cos A plus cos B is equal to, it's not an identity now. It's true for a particular situation, and that situation is if these three angles are in a triangle, right? Let's see what the approach they are. So A, B, and C are angles in a triangle, so they must add up to 180, right? That's a no-brainer here. Divide everything by 2. So A plus B over 2 plus C over 2 equals 90 degrees. Right? You agree so far?
Yes, sir.
Yeah, and the funny thing about this, right, is that I'll tell you what, sometimes you wonder, well, how would I have known this is the approach to solve the problem? But let me tell you, there's no formula. These problems come from, you really have to use all that you know before. You might try them, get them wrong, try another approach. These are real math problems, man. A lot of things you see in algebra and so where you teach a children, you find two numbers when you add them, they get this, and you multiply, you get that. That you can follow it like rote, but not these. These call for real thinking, right? Yeah. Okay. So we are up to the point where it says a plus b over 2 plus c over 2 equals 90. You agree with that? And therefore, they are complementary because when two angles add up to 90, we know they are complementary. Therefore, therefore, and this is something you must know, right? Have you ever heard of this thing where it says the sine of an angle is equals to the cosine of its complement, 90 minus alpha?
Yes, sir.
And
I
you
have to
know,
teach my students that.
yes, cos of alpha is also sine of 90 minus alpha. What wasn't told to you at that level because you didn't know about cot. Remember, you didn't know about sec and cosec and cot, right? You didn't know that. So you weren't told that it is also true that the tangent of an angle is equals to um, the cot of its complement, 90 minus alpha. Right? You weren't told that because well, you weren't introduced to the reciprocal or the inverse, not the inverse, the reciprocal trigonometric functions like sec, cosec, and cot, right? So what you're seeing here then, the tan of this angle is equals to the cot of its complement. That's what that is saying, right? Well, you know, we just proved that this is the same as that. And hence, we have just proven or shown that this is equals to that. Right? So this one came out very easily. Sometimes not all of them will come out that easy. Perhaps you remember, that thing about complementary angles and their special properties and so, right? Good. So, all right. Let's switch over to solving an equation using your knowledge of the factor formula, right? So, let's see. Let's look at this. So, we want to solve the equation sine of 5x minus sine of 3x equals 0. So, with all those techniques that we learned earlier, we just couldn't solve those. Huh? We have an equation like this. None of those techniques that we learned earlier could help you. But the factor formula will help in this case. Right? So we take the factor formula and we write this now as a product. Right? And of course, this is going to be what? 5 and 3. 8 divided by 2 will give you 4 and 3, right? And this whole thing becomes 2 4x sine of 2x upon 2 is x, right? Equals 0, right? That's like how you solve quadratic. If I throw by 2, this 2 gone, right? So cos 4x equals 0. That's what you have here. Or sine x equals 0, right? That equals 0. From that now, cos x equals 0. So, okay, all right, I went the long way here. All right, let's do that. Yeah. So the left theta be 4x, right? So this becomes this. Cos theta equals 0, right? And you find the general solution, right? So when theta equals 0, cos theta equals 0, this is the general solution, right? If you want to look at the identity here, right? This here. And if you were to add, what do they have here? So we have 2n. All right. Let me just explain what it is. Pi over 2 plus 2n pi over 2. Right? That's what it is. This 2 will go with that 2. That 2. So you get pi plus n pi, right? And that's a general solution for cos theta equals 0, if you figure that out. For whatever reason they write it like that, I don't know, right? So this is it. Pi plus n pi, right? So it's the same thing. So cos inverse of 0 would have given you pi over 2, right? And every pi, it takes you to another 0, if you know. What did I do here? I think I did something wrong. Wait. So give me a second. I removed the bracket wrong. 1 second. I just check to see if you're all sleeping. And so when I multiply 2n by this, you get 2n pi over 2 plus pi over 2. Sorry, right? Good. So this 2 will go with that. And you realize that, okay, cos inverse of 0 will give you pi over 2. The calculator is supposed to give you that, right? That's all. And every n pi, the solution will repeat itself. That's why they have this. Not sure why they have it in this form, but wait a minute. The writer put it like that. You get it? So if you put cos inverse in your calculator of 0, you will get pi over 2, I think. And every pi from here to here is pi. From there to there is pi. From here to here to there is pi. From there to there is pi. From there to there is pi. Right? So you're adding pi n pi to pi over 2. Right? So as you change n from -1, -2, -3, that will give you all these solutions. And then when you use 1, 2, 3, 4, and so on, that will give you these solutions, right? Good. So remember, this general solution, which is the same as this, is equal to 4x, but you want x, right? Concept. So we got 4x equals to this thing here. And I was just showing you, this is not the only form it can be written, right? I just showed you that you can write it as n pi plus pi over 2, right? I just showed you that. So all you gotta do is take this and divide it by 4, and you will get the value of x, right? I think that's what they did. I hope that's what they did on the next page. So they haven't solved it yet. Okay, that's what they did. Look here. They took the pi over 2 that was outside, or that is pi over 2 on the outside, yes, and divided by 4. So we get one of the solution as this piece, right? The other one, I think, what was it? Sine x equals 0, right? So the solution for that is n pi, right? Because again, if you find sine inverse of 0, you will get 0. And then you have to add n pi because the solution will repeat itself every pi, right? Every pi going this way. And so every pi. So your solution is x equals n pi, right? So this is your whole solution to the problem. All right, so you saw the factor formula can come in useful. All right, I think most of these here are going to continue along the same line. I'll just go through them. Let me go through this one more. So you want to factorize something like this. looks ugly, but y'all know what you're doing at the CXC level. When I say you group and factorize, you want to group in such a way that when you add the two, like the A and the B, right? You must actually get like an even number so you can divide by 2, right? So notice they put the cos 7 theta and the cos theta here together. Take out the minus sign from this piece, you get two nice values in there, and you use your factor formula. All right, so you take these two, add them, divide by 2, take these two, subtract them, you get 6 theta, divide by 2, and you get a nice value. All right, 2 cos 4 theta, cos 3 theta. All right, so what is it? Factorize it. Isn't it done there? Oh, they aren't finished. They aren't finished.
So this is the first part, the first pair.
Oh, thank you, man. Yeah. Glad you're not sleeping. That's this piece here, right? You get that. And then this
Right.
piece, they're doing there. And they get this, all right, here, right? And then you take this and that, put them together, and factorize out whatever is common. Yeah. Thank you for, yeah, sometimes I myself get drowsy. As I said, I've been doing this thing so long. I need to make this thing into a permanent video. I'll be making a proper video maybe when I get some UG in a place. You don't get rest. You don't get rest. You always got this course, that research, that seminar, that all kinds of things. So you're not getting time to do anything that you really want to do. All right, yeah. So okay, so notice here, when you finish doing all of that, it's not done. They actually take this piece inside here now, and they further apply the factor formula. Oh my, that's what I thought I'm finished. The thing in the bracket now, they further went down now. Apply the factor formula one more time, right? And now you end up with, all right, so I think somehow, let me see what this will end up to be. You're going to end up with 2 times 2 theta sine of theta, right? So this 2 will multiply that minus 2, you're minus 4. This 4 theta is there. This 2 theta comes here, and that comes here, right? I thought the problem was done myself. But it's the factor formula repeatedly being applied all the time to it. You know, we can come right down to that. Very good. Nice. Right. Give me a second. Notice I hear somebody calling by me. Give me 1 second, right? Yeah. All right, cool. So this one is a similar one to what we had before. Maybe we'll do this last one. Yeah, let's go through this last one and then we'll close out. So what did you say? A, B, C, these are angles of a triangle. You are to show that sine A plus sine B plus sine C is equals to 4 cos of A over 2, cos of B over 2, cos of C over 2, right? So let's see the reasoning that you're using. Sine A plus, that's strange. Sine A plus sine B plus sine C is equal to that. Oh, I see a 4 in front here, so I guess that will take care of a lot of things. Changing all the signs to cos. All right. So the same reasoning as before, I think they, no, not, yeah, they're going to come to that reasoning about all of them adding up to 180. Okay. So sine A plus sine B, they take them together, apply the factor formula, right? They take the sine C and they apply the factor formula in this form, where they write it as 2 sine of C over 2, cos of C over 2, right? So factor formula used twice here, on this pair and then on the single C. right? So they go back to that reasoning that if these are three angles in a triangle, they add up to 180. And the same reasoning that a plus b over 2 plus c over 2 adds up to 90. Divide everything by 2, right? Therefore, the sine of a plus b over 2 is equivalent to the cos of c over 2, complementary angles, right? And the sine of c over 2 is equal to the cosine of a plus b over 2, complementary angles throughout here, right? So they're going to write back sine a plus sine b plus sine c. And we're not going to use this one here. We got a plus b over 2, a minus, no. We're going to use now, in the place of that, cos c over 2, right? This cos a minus b over 2, that is retained. Where we see sine c over 2, we're going to put cos now of a plus b over 2. You notice that? And then this cos c over 2 comes back here. Well, I wonder what will happen after that. So what's common? What's common? Oh, yeah. The 2 cos c over 2 is common. So you pull that to the front, and in the bracket is left this piece here. Cos a minus b over 2 plus cos a plus b over 2. Now, they're going back to something. They're saying, but cos a minus b over 2 plus cos a plus b over 2 is equivalent to, what are they saying here? They're applying the factor formula one more time now. It's equal to 2 cos half of all of it, cos half of all of it. It's like another, what do you call it, an iteration of the, or another use or application of the factor formula one more time, right? So what happens with all of that? So you do some, you realize what's going to happen here. This minus b and that plus b is going to go, and you're going to left with a plus a to a over 2. You're going to get half. You're going to get a, and that a by this half will give you a over 2, right? So you get 2 cos a over 2. And same thing you do over here, and you get cos of minus b over 2. Now, one of the things you must know, and maybe from the cos curve, right? The cos curve, because it's symmetric about the vertical axis, cos of minus b over 2 is also equal to cos of b over 2, right? So what are we left with there? So notice, we actually took what was inside here, and we end up getting this, right? So we're going to take this piece and multiply by all of this, and you will get this here, right? Watch it go. You're taking this piece. Remember, we apply the factor formula one more time here, and it simplifies to this. So I'm taking this piece, multiply by this piece, and you will get that. So I think that's what they ask us to show, right? Take some, I mean, the rate at which I explain the thing kind of, you might say, oh, what is the guy doing? What kind of magic I'm doing? But you take it your own time. It's a good brain exercise for you. And trace this thing little by little, right? And you will see that the logic makes perfect sense, right? Okay, good. Yeah, and then you can try some of these. Remember this document that I'm using here? The answers are right at the back, right? At the bottom, the very last page. All the answers are there. You know that you're right or wrong, right? All of these you can. Well, the proof, you won't have answers for those. You have to just know you're proven, right? All right, good. So we will stop there. Friday, we only have this little piece on small angles, which will take less than an hour. And we basically would have covered everything we need to cover on trigonometry, right?